This is the Practice FRQ for Chapter 17, and it's a little complex. Anyway, Part A is not really Chapter 17. It goes way back. It's a stoichiometry problem. So we're going to look at this problem here and pick out the fact that here's our given value. Okay, the 5 times 10 to the minus 3 mole sample of the oxalic acid. And we also have 0.4 molar NaOH, and that's going to be a conversion factor because molarity is moles over liters, or in this case we'll say moles over 1,000 milliliters. So let's go ahead and set this up. We start off with our given 5 times 10 to the negative 3, and that's our moles of the oxalic acid, H2C2O4. Then we can go for every mole of the H2C2O4, we're getting 2 moles of H because this is diprotic. Okay, the heart of the problem really for neutralization is that every time we have 1 mole of H plus, we're going to need 1 mole of OH minus, and then to get from mole to OH minus, we're using our molarity, and we know that they're 0.4 moles of OH minus in every 1,000 milliliters of NaOH solution. So we take all of that, work out all the numbers, and we find out that we get 25 milliliters of our NaOH solution to solve this problem. For part B, this part's a little more straightforward here. We want to write the 2 dissociation equations for oxalic acid. So because this guy is diprotic, so we'll say H2C2O4, double arrow, we get an H plus, and then we get HC2O4 with a minus charge. Then we take that piece, HC2, wrong, go back. Okay, HC2O4, 2 minus, and that will give another H plus, and then we'll have the oxalate ion. So those are the 2 steps right there, 2 points. Now the last part here is calculate the value of the first dissociation constant. So we want to know what is the value for that constant, and we already know that since we have 2 equations that add up to a third equation, so these 2 equations add up to be the overall equation, so therefore we know that the K1 times the K2 will equal the K. So we already know the value of K2, it's given in the problem. We know the value of K, so we want to solve for K1. So K1 is going to be equal to K divided by K2. Okay, K we know is 3.78 times 10 to the negative 6 divided by 6.4 times 10 to the negative 5. And when we're all done that comes out to be 5.91 times 10 to the negative 2. Pretty simple. Part C. Now we have a 0.015 molar solution of oxalic acid. Now this is the one where we're adding some strong acid until the pH comes out to be 0.5. So calculate the oxalate ion concentration. So that's that kind of a strange situation. So first off, the pH we know is 0.5, so therefore the H plus concentration we can calculate. That's 10 to the negative pH, so that's 10 to the negative 0.5, and if we calculate that out, that comes out to be 0.316. molar. Now for this kind of a problem, we go ahead and use the entire overall equation. So we're going to set that up. So the K is equal to the expression, okay, H plus, and this is squared, times oxalate, C2O42 minus, divided by oxalic acid, H2C2O4, and we know that this is 3.78 times 10 to the negative 6. Now from here, we already know that the H plus concentration is 0.316. We are looking for C2O42 minus, and in the problem it states that the concentration of the solution is 0.015. Now officially it's 0.015 minus the amount that dissociates, but the value is really, really small. So we're going to ignore this, and we can go back and see if that was a good idea later on. So setting this up, we have 0.316 squared. That's our H plus concentration. And we got that from our pH. The C2O42 minus is X divided by 0.015. And officially that's 0.015 minus X. That equals 3.78 times 10 to the negative 6. And now this is an algebra problem, so I'm going to leave that for you to do. And we find out that when we're all done, X comes out to be 3.78 times, no it isn't, it comes out to be 5.67 times 10 to the minus 7. And that is our oxalate ion concentration. The last little part of this is asking for what's the Kb if you had a solution of sodium oxalate. So the idea here is the oxalate ion is the conjugate base of the weak acid, and if you put it in water, then it is going to pick up a proton and leave some hydroxides in solution. So this is going to be a base because we're making some hydroxides. Well, we already know that the Ka times the Kb of its conjugate base is equal to Kw. But in this case, we can see what's happening here. We are talking about HC2O4 minus, so we're really talking about the second dissociation of the oxalic acid, not the first one. So if we want to figure out what Kb is, we're going to say Kb equals Kw divided by Ka, and we know that Kw is 1 times 10 to the negative 14, but the Ka we want is the Ka after this, we lost one of the protons when we're losing that second proton. So when this guy turns into this guy. So we actually need to get our K2 to use for the Ka. So let's go back. And we can see that that number is 6.4 times 10 to the negative 5. 6.4 times 10 to the negative 5. And when we calculate that, we get 1.56 times 10 to the negative 10. And that's this problem.